Hi all, this is Mr. Yeager for On-Level Chemistry. On to our next lesson within Unit 1 on the atom. And we are going to now look at more specifically, what makes up the, how do we determine what type of atom we have, and looking a little bit at possibly isotopes and ions as well, and being able to start doing possible activities where you can use a periodic table to identify protons, neutrons, and electrons. I meant to say this in a prior video. These presentations were actually made by another chemistry teacher here. They did not want me to name them out loud, but I just wanted to make sure that they got credit, that they are the ones that created these original presentations that I'm talking about. All right, so this is related to obviously our core standards. I'm going to move on from that real quick. So we talk about atomic structure, and we are to kind of we're going to kind of do our mix of the planetary / quantum structure that we ended up with. We do kind of look at the atom still within a planetary model type shape, where we have the positive nucleus with the protons and neutrons in the middle of the atom, and then the electrons in set energy levels going around the atom. And making it, I know in that model thing we said that it really only worked well for hydrogen. We're going to kind of make a generalization that, it continues on from there. It's just the fact that those rings aren't perfectly spaced. They actually have random, I don't want to say random, but specific spacings that could be larger or smaller as it gets farther and farther out. Okay? So, we are looking at, here's my question. What makes one atom like hydrogen different from another atom like helium? Okay? What really makes one atom different from another one? How do I know that I have oxygen, I have carbon, I have iron, I have gold, I have silver, I have rubidium, any of these other ones that are out there? And the answer is, very, very specifically, it's the number of protons in the nucleus. That is the key, okay? The number of protons gives you exactly how many, gives you exact identity of the element. Every element has a unique number of protons, okay? So, if I show you this picture, what we would do is we could go, okay, what element is this, all right? We could see that there's positive spheres, there's the yellow spheres that have no charge on them, where those are our neutrons, and then we have the electrons going around and around it, okay? So, let's actually put that down for a second here. Let's make it very, very clear here if I haven't done that yet. Okay, you have your protons. Your protons are positively charged and they're in the nucleus. You have your neutrons. They have no charge and they're in the nucleus. And then you have your electrons. They are negatively charged, and they are around the nucleus. You probably have heard the term electron cloud. All right, I'm already going to start pushing the idea that they are in energy levels around the nucleus, because that's going to be something in our next unit that we do quite a bit of. Okay, so if going back and answering my question though, what element is this? I count up the number of positive charges. So 1, 2, 3, 4, 5, 6, 7, 8. All right. This has 8 protons, okay, which will come up on the bottom when I change back. It has 8 protons. Knowing it has 8 protons, it's supposed to be P positive. All right. That I can now go to a periodic table, and once we learn how to read a periodic table, which you're going to be able to do very quickly, I have no doubt, you'll be able to identify that this must be oxygen. The only element that has 8 protons is oxygen, okay? Which is what it has. There you go. All right? So, this leads to one of our first very important terms, the atomic number. The atomic number is the number of protons in an atom. All right? It is just a number. There's no calculation. Okay, it is clearly shown on the periodic table. I'll show some pictures of that in just a second. All right, it is on the periodic table. The atomic number is the whole number, so not a decimal, in the elemental box. Okay, and again, I'll kind of show you a picture of that. Elements are arranged according to increasing atomic number on a periodic table. All right, So that is the arrangement. We do another unit about how we created the periodic table. This is the most modern version again, where we start at 1, go 2, 3, 4, 5, and it's all based on number of protons. Okay? So this is sort of what you'll see. This isn't all the information on periodic table, but this is what you would see, is you can see you'll get an element, okay, and we'll kind of go over this. I'm going to switch to another slide in a second. But the number that is on top, or usually in the top left or right corner, all right, of periodic tables, because people make periodic tables lots of different ways, that whole number is the atomic number, and it's telling you the number of protons. And each one will be above a different element, okay? So what we have here is this is showing you hydrogen, this is helium, and this is lithium. Lithium has 3 protons. Helium has 2 protons. That is the atomic number. That is what's telling you what element you have. Every element is unique in that way, okay? So, I'm going to go back for a second here. I'm going to go to another presentation that I have. So, this is what you would basically see on a periodic table, okay? This is usually the 4 pieces of information. Again, there are other ones that actually don't even show all this, but this is generally what you'll see. Each element is in its own little, like we said it in the notes, elemental box. And so usually what you have is you have the element name clearly spelled out for you, so you don't spell it wrong. Okay, this is calcium, all right? Usually one of the largest things on the periodic table in each box is an abbreviation of the element. We call this the chemical symbol. Okay? The chemical symbol. And it is made up of either 1 or maximum 2 letters that tell you what element it is on the periodic table. It is our way of being able to say, and we're going to see writing out compounds, writing out chemical reactions, instead of writing out the full name of it. It's our way of notating the element so that we can write it a whole lot faster, okay? Usually, okay, there's plenty of exceptions, unfortunately, though, okay? Usually, it's either the first letter or the first and second letter of the element name. So we have calcium there, okay? As we saw, hydrogen, its chemical symbol is H, okay? There are some, the other thing I want to say about chemical symbols, the first letter is always capitalized. If there is a second letter, it is lowercase. If you write Ca, we will read this as that's one element, and then you're trying to tell me that's a second element with it. Okay, that this is 2 elements. All right? And one reason that would be wrong is, one, while C would be carbon, there is no atom, no element with just the letter A. Okay, there are ones that have A in it, but it's a C, a T, different ones like that. All right, so you have to write the first letter capital and the second letter lowercase. As I said, there are some weird ones. These are ones that were known to the ancient Greeks and ancient Romans. So, one common one that we will be using is K, and K is potassium. And you might be sitting there going, what the heck? How did that happen? I mean, the K is not even in it, and that's why I said there are exceptions. All right, some might make no sense. And it goes back to what the ancient Greeks and Romans used to call this element, because again, they knew about certain elements. They thought they were just these solid spheres. And the name of potassium at that time was called kalium. Okay, and so that's where we get K. It's the same thing with gold. Gold is AU. They knew gold, they used to call gold aurium. Okay, and so that's why it makes sense, technically, okay? Just not so much to us because we don't know those original, we don't use those original names. Okay? All right, back to the other notes. All right. Now, this is kind of a nice thing for the moment, okay, even though we're going to immediately kind of play with this. We make a general assumption that atoms are all electrically neutral when they start off. And when we say electrically neutral, we mean that they have no charge. Okay, that's what we're saying. There is no overall charge to an atom. Initially. Okay? The nice thing about that then is it tells us that the protons and neutrons are equal to each other. Okay, they are completely equal to each other. So if I say how many electrons does helium have, I could go helium has an atomic number of 2, which means it has 2 protons, which means it has 2 electrons. So once again, no math yet. All conceptual understanding that, hey, this is all we have to do with it. That's all equal. Okay, so protons and neutrons for the moment are equal, and then I'm immediately going to change that. Okay, so here's it kind of showing through some examples. Just letting you look at that for a second. Again, they're getting the atomic number from the periodic table. That's the protons, and then the electrons are equal to it. Now, one thing I will say is the definition of the atomic number. The atomic number, the definition is it's the number of protons. Okay? The atomic number is not the number of electrons. It's just when the atom is neutral, they're equal to each other. So the atomic number is equal to the number of protons, which then happens to equal the number of electrons at this moment. All right. Well, let's immediately get rid of that because most atoms do not occur naturally neutral. Okay, they immediately lose or gain electrons. So what happens when atoms are not neutral? They become what we call ions. Okay, ions are atoms that, as you see there, have lost or gained electrons in order to, we will get a lot more into this, satisfy what's called an octet rule. Okay, it turns out all atoms want to try to have 8 electrons in their outermost energy level. Okay, it's called a valence shell. We will get to that in another unit. All we need to know is if I gain electrons, I become negative. If I lose electrons, I become positive, and that we can already start identifying charge. Okay, so again, if an atom turns into an ion, the protons and the electrons are no longer equal, okay, which means it's no longer neutral, and it is an ion. All right. Now the nice thing is atoms usually only gain or lose 1, 2, or 3 electrons. So we don't go much farther than positive 1, positive 2, positive 3, negative 1, negative 2, negative 3. There are exceptions. Again, there's plenty of exceptions in chemistry that we don't get to at this level, but we can kind of stick with that amount. Okay? All right, so you can see, I guess I'll get rid of that so you don't see it. We have calcium, and you see a +2 written almost like an exponent on it. Okay? What this means is calcium has a +2 charge, which means since it's positive, it must have more protons than electrons. Well, if they were initially equal to each other, I can't change the proton number. If I change protons, if I add protons, it won't be calcium any longer. So the only thing I can really mess with is the electrons. Okay? We only mess with electrons. Here, I'm going to draw more arrows to show that we only mess with electrons. Okay? And what this is saying is, if calcium is +2, it must have lost 2 electrons. Okay, and I know that can be confusing because you're like, I lost, shouldn't that be negative? The electrons are negative. If I take away an electron, I have more protons. Protons are positive, and therefore, that's why I have a positive charge with this. Okay, you can see the second example here that Na+, you're going to see we usually do not write the 1. Okay, that means this atom has lost 1 electron. Now we do give this a special name for positive. Positive ions are called cations. All right? Sometimes people write it like this to remember. Cation, positive, okay? So that's what we're looking at there. So a cation is something that loses electrons, becomes positive, and the number of electrons it loses is written as a positive with the number next to it. Okay? If you become negative, that means I must have gained electrons. Again, don't touch the protons. Please don't touch the protons. Okay? It becomes negative because it pulls in electrons and it takes on more of that charge. We call that an anion. All right? They have gained electrons, they have gained negative charges, and therefore they will take on a negative superscript, exponent, whatever you want to call it. All right, last thing, isotopes. Isotopes. We mentioned this briefly in the model presentation, model video, okay? Isotopes are atoms that have the same number of protons, meaning that they are the same element, okay? This is the key thing. They have the same number of protons. They are the same element, but they have a different number of neutrons, so they have a different mass. So isotopes are the same element, but with different masses, because they have different number of neutrons. So that leads us to, oh, sorry, I was getting ahead of myself. So the number of neutrons can be different for an element, because again, we already said the protons is what tells us what type of element we have, okay? But there can be different number of neutrons. Neutrons can change. Usually they don't change by much. Usually it's like this atom has one more neutron than this atom. You can see that in my example. One atom has 20 neutrons, another one has 21, another one has 22. Okay? Every single one has 19 protons, and if we're assuming they're neutral, they have 19 electrons. Okay? It's only the neutrons changing. So again, just like an ion, the atom, the element is not changing. I am changing either the charge or, in this case, the mass. And that leads us to what's called the mass number. Okay? The mass number, this is finally your first little calculation. It's a simple addition or subtraction, depending on what you're trying to do. Okay? The mass number is simply protons plus neutrons. Protons plus neutrons is the mass number. Now, this is not on the periodic table. I'll go back to it to finish up this video in just a moment. But the mass number is not on the periodic table. It is not on it. All I can tell you is don't try to find the mass number on the periodic table. It is not there. It is something that I would have to give you, or I give you the protons and neutrons and you'd figure it out. Okay? Is what we'd have to do. So you can see some of the calculations here, and I'll probably do another video where I show some of the calculations with this. If I have potassium 39, this right here, when I write it this way, this is telling you the mass number. Okay? When I write out the element and then a number after it, that is the mass number. Okay, there is another notation, I'll get to that in a second. What you can do is you can go potassium. You look up on the periodic table, you would find potassium, I said that was K, and it has a 19 above it. This is the atomic number, which is the number of protons. So if the mass number is 39 and 19 of the 39 is protons, that must mean 20 must be neutrons. So you would do 39 minus 19 equals 20. Okay? Some people like a formal formula if you want to write it down. The mass number minus the atomic number equals the number of neutrons. Okay? That's how you can do it as well. You can see another type of notation here. This is a second type of notation. If you see this notation, the smaller number, you have your element, your chemical symbol. The smaller number is your atomic number, and the bigger number is the mass number. Always, always, always. Again, you should be able to confirm that on the periodic table, that K is 19. Okay? So you can just subtract those two, and then that'll figure out your mass, your number of neutrons. All right? Last kind of point here, and then I'll just show a couple other quick things. We do give units to this, to mass numbers and atomic numbers. The unit for it is called the atomic mass unit, AMU. And we basically say every proton and neutron are approximately the same mass. Technically, a neutron is ever so slightly bigger than a proton, but it doesn't really matter in our calculations. And we say 1 AMU is equal to 1 proton or 1 neutron. So the example with the K, if I said what's the mass of K, it would technically be 39 AMU, because we have 19 protons, so 19 AMUs plus 20 neutrons is 39. Okay, so that's what you'd be looking at there. So let me point out one other thing, and maybe we'll do just one or two other problems. Whoops, too far there. Going back to my other presentation. I just want to point this out right now so we understand. Again, this is what you see on a periodic table. We already said chemical name, atomic number, chemical symbol. What the heck is this thing? Okay? There will be a decimal number, I'd say a number with a decimal, usually underneath of it. I think this is usually what the type of periodic table I give. This right here is not the mass number. The mass number is a whole number. This right here is something we're going to call the atomic mass, which is I'm going to go over in the next video. Okay, sometimes it's called the relative atomic mass. This is not the mass number, even though I know somebody's going to try to make it the mass number. Okay, so you do not use this number. You are not going to really use it all for a while in this class. It'll come up very important later on, very, very important later. But for right now, this is a fairly worthless number to at least use in any sort of calculation. Okay? It is the relative atomic mass. All right? So let's do a quick problem with this one. Let's say, for instance, with calcium, because this is kind of what your work will look like, I want you, oh, that's silly. I want you to write down the chemical name. Sorry, I should say the element name. The element name, the chemical symbol, the atomic number, the number of protons, the number of electrons, the number of neutrons, and the mass number. Okay? All right. Now, I'd have to give you at least one other piece of information. You cannot get all of this looking at the periodic table. It's impossible. You cannot do it. You cannot do it. I hope you understand that. You cannot get all of this. You can get a lot of them, but there will be two things you can't get. So I need to give you one of those at least in any problem. And I'm going to go and say that the number of neutrons in this calcium atom this time, I'm going to make it 22. Okay? All right. So now you can answer the rest of this. So the element name is calcium. The chemical symbol is Ca. Make sure I write capital C, little a. The atomic number is that whole number at the top, 20. Well, if the atomic number is 20, the number of protons is 20. Well, if I have 20 protons, and again, I don't say anything about ions in here, so I'm assuming this is neutral. The number of electrons is 20. Remember, these two are equal to each other. All three of these things are equal to each other. And all I have left now is the mass number. Mass number is protons plus neutrons. Well, how many protons do I have? 20. How many neutrons do I have? 22. So my mass number is 42. Again, this is nowhere on the periodic table, so you'd have to figure this one out based on the information I give you on your own. Okay? So this 40.078 does nothing for us. Get rid of it. All right? That's it. Very, very good. Very important stuff for being able to identify elements, identify all the particles in the element, which is going to be a big part all year long.